All right, very good. So it is now being recorded. And the speaker today is CongXu, who is Thomas's student at UC Davis. And, as you can see from the title slide, I mean, he's been working with Moritz, Thomas, Andreas, and me um, on a change point, four-dimensional change point detection. So without further ado, take it away, Kong.
Okay, so let's get started. And today we are going to mainly talk about this change point detection problem. And so we'll start with the background of the problem and also the way we model it. And then I will try to present a practical algorithm to deal with it. And so finally, some applications to some real data sets. Okay. So the first one, let's look at the background of this problem. So it's pretty common that we are interested in some time varying phenomena. So in this astrophysics background. So, and the thing we are interested in is, so we want to detect change points in the time direction, which means the time at which we can see some sudden changes happening. So, and also apart from detecting the change points, we also want to identify the source of the astronomical object, and also we want to locate the spatial boundaries. So after taking all these things into consideration, so the change point actually means it can be the intensity of the source changes, the shape of the source changes, or some other changes. So all of them, we want to detect these change points. Okay, so we start with dealing with the raw data set into something we want. So usually what we obtain is a list of photons. So we have some informations about them. We know their spatial coordinates when the photon was detected. So we know the X and Y. Also, we know the time when they were recorded. Also, their energy, or equivalently, their wavelengths. So we have a four-dimensional thing. So we have all this information. So that's why we call it 4D Automark. So because we have a four-dimensional information about these photons. Okay, so first thing, we want to bin this data set into a 4D rectangular grid of boxes. So based on the two-dimensional coordinates, time, and also the energy. So finally, we have a 4D table of photon counts. So, and the indices are two-dimensional coordinates, time index, and also the energy band. So after this kind of binning, and this new 4D table can be viewed as a series of images. So because we have a two-dimensional coordinates, so it's like an image, and it has different energy bands. So it's a multi-band images. This just like the RGB image, it has three bands. So in this case, there's a multi-band images. And so a series of them because we have time indices. So from the starting time, and it has a time series of multi-band images. And the values in this image are the photon counts. Okay, so that's the first step. So we bin the original list of photons into this kind of 4D table. Okay. Okay, so right now, that's the first step. Now we want to add some assumptions onto it so we can model this whole process. So first one is pretty obvious. We assume that the emission times of photons can be considered as a non-homogeneous Poisson process. So actually, For all these observations, for all these pixel values, they can be treated as Poisson counts. Um, so these Poisson counts, and they are independent because these grids do not overlap with each other, so they are independent. And therefore, the different images at different time points, they are also independent. So yeah, then that's to say that for all these pixel values, so here we denoted by YITW, here I denotes the index for the location. So we just use one index instead of two to denote the spatial coordinate of this index. So I denotes the location, and the second index T denotes the time points, and third one W denotes the energy band. So this YITW, and so each of them is a pixel in the images. They are, oh, it shouldn't be IID, sorry. So they are independent. Mm, they are just independent. They are not identically distributed. So they are independent, has a Poisson distribution with some underlying unknown parameter lambda ITW times the duration of this time point, so which is called the exposure time. So, so in terms of the Poisson process, we can view that lambda is the corresponding Poisson intensity, and this delta t means the corresponding duration of this process. So that's how we model this whole thing. So we have a series of multi-band images, and these pixels are independent Poisson counts. And right now the goal is to estimate the underlying Poisson parameter or Poisson intensity lambda based on what we observed, this wise. So that's the whole thing. And so right, the other important assumption is that, so we just assume that the underlying Poisson rate, these lambdas, for each of the image follows a piecewise constant function, which means that we just add some structures onto this lambda. So we do not allow lambda to be changed freely. So we have some restrictions. We assume that they are, this one is actually a piecewise constant function. So now I'm going to mention the details about this piecewise constant function assumption. So we start with a simple case. We just assume that there's no change point, which means all these lambdas does not change with respect to t. So for different t's, they are actually the same. So we assume that we first consider a temporally homogeneous Poisson model without any change points. So therefore, in this case, each image can be treated as independent Poisson realizations of the same unknown true image, because we assume that lambdas does not change over time. So that's the same unknown true image. Okay, so therefore we can actually write it in a rigorous way. The lambda ITW can be written in this format. So the idea is that we can partition this two-dimensional space into m non-overlapping regions. So it's here h from 1 to m. So there are m regions. They do not overlap with each other. And all of them compose a partition of the whole space, the whole two-dimensional space of xy coordinates. And for each region, it has all the pixels in the same region share the same Poisson intensity. Here we use mu to denote that. So H denotes the index for the region, and W is the index for the energy band. So for the pixels in the same region, they share the same Poisson intensity. And the second part here is so it denotes that so whether the index I belongs to the H region. So if I belongs to that, then this function, the indicator function takes value 1. Otherwise, it takes value 0. So the whole space is partitioned into non-overlapping regions, just like that. So that's the case when we assume that the model is homogeneous, which means, well, here, actually the time doesn't matter because for different time points, the underlying model is the same. So right now, we just want to add change points into this model. So right now we assume that these images, well, this series of images can be partitioned or be segmented into different time intervals. So by k change points. So we have tau 1 to tau k, they are k change points, and therefore the whole series of images has been partitioned into k plus 1 time intervals. And we assume that for each of the interval, it has a homogeneous piecewise constant model, as we mentioned before, like that. So therefore, we can write down the formula for this lambda in this format. So first is the segmentation over time, so the partition over time. So it has k plus 1 time intervals. And for each of the interval, it has a model like that. It's the two-dimensional xy coordinate space has been partitioned into mk regions. Each of them has its own Poisson intensity and the corresponding indicator function. So that's the model. So we have some change points, and for the intervals determined by these change points, it has a piecewise constant like that. Okay, so right now the goal is that given the observed image y, we want to estimate the unknown Poisson parameters lambda, and we assume some structures with respect to lambda, which means we want to estimate the location of the change points, these taus, and also this the partition of the regions, and also the corresponding Poisson rates for all of these regions. So right now, so assume the case, if we know the change points as well as the image partitions, then the Poisson rate can be easily estimated by, for example, the maximum likelihood estimation. So it's just pretty simple after giving the change points and the image partitions. Okay, so but the problem is it's pretty hard to estimate the change points and the image partitions given just this 4D table like that. So estimating the partition is actually a quite complicated model selection problem. So it's kind of like a combinatoric one. So therefore, we need some criteria or principle to help us to estimate this partition or image segmentation part. So here we will use the one called MDL, the minimum description length principle, as the criteria or the loss function for the estimation of the change points and the image partition. So some backgrounds about this principle. So we can see that for the same dataset, there can be many models to model this problem. So, but here, MDL defines the best model as the one that produces the best lossless compression of the dataset. So here, we use code length to denote the result of the compression. So which means we want the code length to be as small as possible. So the code length uh, can be viewed as the amount of hardware memories to store these things. So then we can see that for a given model, the MDL can be viewed as the code length. First, we want to encode the model, and then we want to encode the data given this fitted model. And the summation of these two parts of these two code lengths is the corresponding MDL for this model. So we can see that for different models, they may have different code lengths to encode these models. And also they have different code lengths for the data given the fitted model. So therefore, we can compare different models based on this MDL. And the model with smaller MDL is better than the other. And now let's look at some details about this criteria.
Kong,
Yes.
I have a quick question.
Yes.
So I guess using this MDL sort of assumes that there is there's a guaranteed minimum in this curve, right? I mean that there is some sort of trade-off between the fitted model CL versus the data given fitted model CL.
Yes. And the second term, yeah.
Yeah. So, I mean, is that guaranteed?
Yeah. Usually there is a trade-off between these two terms. So usually we can use that one to compare different models, and so we're talking about the.
So is this like a bias variance trade-off?
Yes, that's true. Yeah.
Okay.
Renee, sorry.
Go ahead, Shirley.
No, I was just going to say that this one always puzzles me. I talked to Thomas quite a bit of time. I think there's still something very mysterious about the MDL principle. It apparently certainly has been working quite well, and for me it's always very puzzling why the description, why the hardware memory, right? That's something human invented, right? Why that matters? How God operates of those things, right? But there are clearly something hidden. There's something about the complexity which I don't quite understand, and so I think that this is meant to be like a bias variance trade-off, except that the fundamental reason why the MDL works that I still don't quite understand, and I've not seen a very clear description why. There's something very mysterious about it. So I want to mention that.
So,
to be fair, that's true of things like AIC and BIC as well. There's a lot of these kind of methods around that are a little ad hoc, but seem to work reasonably well in practice.
But at least AIC, BIC, has this notion of overfitting of those, like you will see, right? We have a little bit more better understanding, not in kind of rigorous theoretical sense, but this is why the hardware memory matters, right? Why
why is that even in the formula?
Right. Why even that? I mean, someday somebody invented something entirely new, computing methods like no longer have this memory. I don't think that would be true, but just sort of hypothetically, why this governs? But apparently there's something to it. David, you probably would appreciate this. I have been wondering whether this is the kind of thing like there's some coincidence. It's like how the EM algorithm, its speed is controlled by the fraction misinformation, which happened to be also an information measure, right? So if somebody, remember we almost did a paper on if a mixture is fitting slowly, that probably the mixture is not fitting well, right? That just because of this same measure, the Fisher information measure both the algorithm speed as well as the information in the data. I've been wondering when this kind of MDL has, not the MDL itself really matters. It's because they both are controlled by something more fundamental that linked to them. Yeah. Anyway, but it's always very, very interesting. And Thomas is very good at counting these I'm going to learn how to count these memory storage.
Yeah. So I think that's how we define a good model. So it should be as simple as possible, and also it should somehow capture the nature of the underlying story of this data set. So it can be viewed as the summation of these two terms, but I don't have pretty good explanation for that.
Yeah, I have another comment, which is
Yes.
related to this. I was just thinking about this Fermat principle, where you have the light going, and you always the light travels on the shortest length. So I'm just wondering if there is any connection between this MDL and this Fermat principle, which
Action.
yeah, there must be, right?
That's actually good insight, because nature does operate, like nature knows how to minimize the energy, right? Like all the protein folding on the problem. So maybe the way to think about, that's a good point. Think about nature itself is like a hardware, like well, it is, right? It is in a way. It's hardware and a software, and somehow nature has a way to find the minimum energy. And here is the kind of that might be a really good way to thinking about that. There is a physical reasons for this thing works as it should be.
I mean,
it is a point.
Yeah, it is a question of why this works. Yeah, that's the philosophy too. It's just, okay, that's the comment.
Yeah, thank you.
I have a question. So it's a silly one. I just wanted to clarify my understanding. So the amount of hardware memory, in the sense you're talking about the system's RAM speed, or
it's kind of like the how many bits we need to encode it.
Okay, so if I interpreted correctly, then larger the hardware memory, then better the fitting, or?
So the smaller it is, the better the model is.
Okay.
Yeah.
Okay, thank you.
Yeah. Okay, so let's continue to talk about this one. So we can see that it's the summation of two terms. The first one is the code length to encode the fitted model. So we can imagine that if the model is very complicated, then this term will be large, because it needs just more information to encode it. So the first term is actually the model complexity. So the larger this term is, the more complex the model will be. And the second term, the code length for the data given the fitted model. So the idea is that if the model fits the data pretty well, then this term will be small. So actually that's called data fidelity. And actually, so this person, the researcher who invented this principle, just derived that actually this term, the second term, is actually the negative log likelihood of the data given this fitted model. So which means that if the model fits it pretty well, then the second term will be small. So yeah, the model complexity plus the data fidelity. So that's kind of like this principle, what this principle means. So
I have a question here. Is this result, since I'm not familiar with the literature, is this negative condition log likelihood is exact results, or it's a kind of approximate, like asymptotic results of what's the nature of this this term?
It's kind of like using something about the information theory. So how it's kind of like how could we encode these residuals given this model. So this one tends to be the log likelihood.
Is it more like a kind of entropy type of, like Shannon?
Yes. So like the information theory, this kind of stuff.
Okay, I see when they said it's KL diverge, I see. Log entropy, yes. I think that's probably okay.
Yeah, so okay,
Can I ask one quick question? Yeah, this is just but is it two terms should have an equal weighting, or you can allow the sort of relative weighting? You give a little more weight on the fitted model code length versus second term. Can you allow that, or?
Usually we don't do that because it has a meaning for these two terms. They are just code lengths, so we just add them together. So in practice, we don't really add a hyperparameter to reweight these two terms.
Okay, thanks.
Yeah. So yeah. Okay. So anyway, so we can use this principle to compare different models. So the one with the smallest MDL can be viewed as the best model in this case. So yeah, that's this. Okay, the reason why we use MDL. So first one is computationally trackable for this kind of complicated problems. And second part is that so MDL can be used to some other model selection tasks. For example, the time series, just the images, and or some regression problems. So it has been shown to enjoy pretty good theoretical and empirical properties for these other model selection tasks. That's why we use MDL here. Okay, so right now we still need a specific formula for the MDL. So we follow the method from Thomas, and the MDL for a homogeneous model can be written in this way. So pretty complicated, but now, okay, so the first three terms is actually the first part, which denotes the code length to encode the fitted model. And the last part minus this one is actually the log likelihood term, sorry, negative log likelihood term. So given this model. So we can see that the first term has M, which means the number of regions. So obviously, the more regions it has, the more complicated the model is. And it also has some terms like AH and BH. So actually, AH denotes the area or the number of pixels for each of the region. And BH is the perimeter or the length of the boundary for each of the region. So usually the more, if the model has many regions and the regions look so pretty weird, then in that case, the first term, the whole thing will be large. So the more complicated the model is, the larger the first term will be. And the second term is just the negative log likelihood. So if the model fits it pretty well, then this term will be small. So the summation of these two terms. That's the MDL for a homogeneous model with no change points.
So let me ask you that the second term obviously is very familiar to log likelihood, negative log likelihood. First term, again, is this some kind of exact calculation or it's approximation? And can you explain how that was actually done, or just this is just from Thomas' work, or you actually did this calculation, the y like where the log 3 comes from, for example?
Log 3, yeah. So so the second term, this part, denotes the code length we need to encode the boundaries for this region, for these regions. So for example, so let's say, so we have a region with a given shape. Then the way we encode it can be used as so we start with a point on the boundary and we just go through the whole perimeter clockwise or counterclockwise. So then we need to encode these steps. So for each step, you go up or down, left or right. So we need this kind of thing to encode the whole boundary for a region, right?
Right, but that's where I'm not get confused, right? Am I correct that how to code it would depend on who's coding it? So therefore, you could have different lengths, but the model is the same model. So does this MDL principle will depends on the person how to implement it?
Yes, it
or this
did.
region has the region has a unique way to code it, or maybe the criteria is have to be the code has to be the most kind of efficient code. It's like the minimum code to start with. Because somebody like me could have coded terribly, right? Could have wasted lots of bits, right? And so what's the requirement there in terms of putting like the formula there? Is this like the best you can code?
Actually, the way to encode it is not unique, of course, and so actually we don't really have a pretty solid standard to determine how we code it. Yeah.
Interesting.
Yeah.
But the results will be whether the good model or not will depends on how you actually code it, which is seems a little bit odd.
Kind of, but anyway, at least we use the same criteria for all the different models, right?
For you, yes. Within the same paper, you're okay. I see the point. You say a relative comparison. Okay. Again, I think this just reflects that we don't quite fully understand why these methods work. Like the second term is quite clear. Second term is log likelihood, so it's a derivation from the coding, but you don't have to believe the coding, right? Just think it's log likelihood. But the first part seems like it's much more nuanced. Depends on who's doing it. Right?
Kind of, yeah. So there are many ways of encoding this kind of thing.
But isn't it the case that regardless of what you do, as long as you're using the same formula for all the different boundaries and everything, a circle is still better than, takes less description than a polygon?
But that has a requirement, right? Like someone like me, like do something completely stupid, it will not have less requirement. I could do something really bad, right? so the Gabi, this is like, I think this Gabi, like, for the people in this field, that there is a best way of code it. Right? The whole idea is to minimize things, so you cannot waste it. It's something like it's a boundary. But among all these ones, you can best code it. How do you compare them? I think there got to be some efficiency requirement there, right?
Yeah.
But correct me if my understanding is wrong. So, so the best, for example, if you have two sets of coding for the same set of image, this the comparison or the difference with the log likelihood should be the best estimator to say like which one gives you the best estimate, right?
In the whole thing?
Yeah. So in the equation, the first three parts is defined by the coder or the how good the model is, and the log likelihood is basically the difference between that. Should tell you that whether you're minimizing it or not, or how good you minimize the difference. Am I right?
Actually, the first three terms is the code length for the fitted model. So if a model is complicated, the first three terms should be large. And the last one is the negative log likelihood. So if the model fits the data well, then this term will be small. So when we determine whether a model is good or not, we need to combine these two parts of information together. We want it to be the model is not complex and the model fits it well. So that's the idea.
Okay.
So I think the point though is that once you define how you get the BH, you can't change it in the middle of the problem.
Yes. So in practice, we just use the same way to compare all the different models.
Okay, but when you say that how we compare the models, my question is like, how do you gauge that this model fits better than, so that you do it before you get into this MDL?
So the idea is that given two models, how can we compare them? Yeah. So so once the model is given, so we know the M, these R, these mu's, then we can just plug them in and get two values. They can be calculated from the given model and the data set. And so we'll just choose the model which has a smaller MDL value.
So maybe, Atre, the way to think of this is this is a different formulation of using the chi-square, I mean, or a C-stat. And the terms are different, but it gives you a sort of, when you compare two models, it's going to give you two different MDLs, and you pick the one with the lower value.
Least, yeah. Yeah, it's a similar. I agree with you when I am trying to think in that terms, which we are familiar with using.
Yes, exactly.
Yeah, exactly. We have been using that, so it's a variant from the C-stat or the conventional minimization procedures. Okay, thank you.
Okay, so two parts: the columns for the fitted model and the data given the fitted model. Okay, so that's how we define the MDL. So the best model is one that minimizes it. Okay, remember this is the case one, the the homogeneous case. So there's no change point. And right now we need to extend it into a more complicated case that we can have many change points here. So the overall MDL criteria actually is for the model with change points. This one can be written in this format. So the first part is the code length to encode the locations of these change points, and then just plus the MDL, like here, for each of the time interval. So still it can be viewed as the code length to encode the change points, the code length to encode all these image partitionings, and code length to encode all the Poisson parameters. And also the next first plus the negative log likelihood for all the things. So that's the overall MDL for the model with change points. So actually that's kind of like the loss function or the objective function we are going to minimize. So the best model is defined as the minimizer of this criteria. So that's one is the loss function. Okay, so that's the whole story. So what is a good model, and how could we evaluate different models? So we base on this MDL criteria. So and right now the goal is that, so given these observations, yi's, ytw's, we want to find the model that such that this value is minimized. Okay, so just a small part, so we can somehow show the MDL-based model selection procedure is statistically consistent under some assumptions, some mild assumptions of the underlying true Poisson parameters, lambdas. So I will skip this part. So right now we are just going to talk about the practical algorithm, that how could we, in practice, minimize the MDL and find the corresponding model. So the global minimization of MDL is kind of virtually infeasible because, so there are many possible models. So we need to determine the change points and also the partitioning for different time intervals. So the global minimization is like a combinatoric thing. It's just impossible to get a global minimization. So especially when the number of images and the number of pixels are not small. So instead, we are going to do something approximately. So we want to use some kind of greedy algorithm to help us to find a local minimization of the MDL. So the idea of the minimization algorithm is illustrated in this plot. So the idea is that first we start with a given set of change points. So the change points are given. So we know there are some intervals. These intervals are also given. So then for each of this time interval, we just pick these images we pick the images in this case time interval, and we use some algorithms for start with city region growing and merging these regions. Then finally, we get the image segmentation. So for the case time interval. So we'll talk about this part later. And so first we get a image segmentation for the case time interval. And this one is kind of like the minimizer of the MDL in that part. And then we just need to, put all of them together. Then we can calculate the corresponding MDL for this set of change points. So for this set of change points, we have a given MDL for that. Then we do some backward elimination. We just iteratively remove a change point such that it produces the best improvement in terms of the MDL. So it's like a greedy algorithm. So we start with a set of change points and fit the model for the get the MDL for this one, and we iteratively remove one of them. So finally, we get the model during this procedure. We get the model with we get a sequence of models, and we just pick the model with the smallest MDL. Okay, so in detail, so we given the set of change points, we calculate the MDL criteria, and we modify the set of change points. For example, adding or removing one of them. And we update this set of change points and get a new MDL for this new model. And
sorry, I have a question. So
yes,
temporarily, do we assume something that the change points are not varying? Or
sorry, where?
Can you go to the previous slide? So you have an assumption on the time temporal variation, right? In the previous slide you mentioned, I missed out. In the previous one?
This one?
Yeah. Okay, my question is like every time when you go through this minimization loop iteratively, so you for each time interval you identify the change points.
Not the change point. So given the change points, the images in this interval are actually homogeneous. So what we need to do is just to do the image segmentation.
Okay.
I think if I can translate. So suppose you have a light curve of images, a data cube, right? So you first say, let's say that suppose there are 100 such images. Let's say you say that there's a change point at the 50th image. That is a model. And then you go through this whole thing, you calculate the MDL. And then you add another change point at the 75th slice. And then you calculate the MDL for that. And if it's better, then clearly it's a better model.
Okay. Now that makes sense. Yeah. Thank you.
So the time and the change points are different.
Okay. Yeah. I got confused. I'm sorry.
Is that right, Kong?
Yeah,
I'm not sure I actually did that right.
Yeah, that's exactly the idea.
Yeah, I'm sorry, I got confused. So I just wanted to get the clarification. Thank you.
Yeah, so it's an iterative algorithm. So for the whole procedure, we maybe add a change point, get a corresponding MDL, add another change point, get an MDL. So for the whole procedure, we have a sequence of models with their corresponding MDLs, and we just pick the one with the smallest MDL.
So, sorry, do you assume that the number of change points are known a priori?
Not, we don't assume that. Yeah, okay. So we can say that, so this part is kind of like a penalty for the number of change points. Yeah, so
I see, okay.
So we can use this criteria to determine the number of change points, the locations, and everything.
I see. So it will penalize for having too many change points.
Yes.
Okay. Got it. Thank you.
Okay, so right now the problem is that, so we can say the problem is that given the change points, how could we fit the model within this time interval? How could we do the image segmentation for this time interval? So, so here still we need to use some greedy algorithms to help us to find the minimization, because global minimization is still infeasible. So we start with this kind of thing. So it has two steps. So first, we want to find an initial over segmentations, which means there are many regions. There are much more regions than it should be. So we find the initial over segmentations. And then we just keep merging the neighboring regions and to appropriate final image segmentation. Then that's the model for this time interval for these images. So we start with the initial over segmentation, and then we merge the neighboring regions. So for the initial over segmentation, we use the method called city region growing. The idea is somehow like that. So first, we start with some initial seeds. So we can pick the seeds manually or with some algorithms. But okay, first we start with some seeds in this whole space. So right now, so for each of the pixel, it might belongs to one of the seed or it's unlabeled yet. So, and every time the seed will grow somehow. So for example, for each of the seed, it has 4 neighboring pixels like that. And so now first they need to determine which one is kind of like the closest to any of these pixel. Suppose it's this pixel. Suppose this pixel and this first seed is pretty close to each other. Then the first seed will grow to the right-hand side. So the region just keep growing like that. Yes, so right now this pixel is labeled and the region has some more neighboring pixels like that. So every time we just do the same thing. The region just grow such that the pixel and the seed is close to each other. And finally, these regions just covers the whole space, which means there's no unlabeled pixel. And then that's the final result. That's the final initial over segmentation. So we just first we select a set of seeds, and then the seed comprises as an initial region, and it keeps growing outward until the whole image is covered. So at each step, we just compare these pixels with the set of candidates as neighbors to grow in the region, and we pick one and merge it into the region based on the similarity. Or in this case, specifically, we use it based on the Poisson likelihood. And this process just repeated until that all these pixels has been labeled. So the whole image can be partitioned into different regions like that. Then that's the initial over segmentation. Any questions about this part? Okay. So start from the over segmentation. The next step is to do the merging. So at each step, we just choose 2 neighboring regions and merge them into one region. So such that this merging provides the largest reduction in the MDL. So, and we just keep doing so. So suppose initially we have M regions, then we just keep merging 2 of them, and we have a sequence of models. Then finally, all these regions are merged together. So there's only one region. So we have M models from M regions to only one regions. We have a sequence of models, and we just choose the model, this segmentation with the smallest MDL. So for example, initially there are 4 regions like that. And for every iteration, we just merge two neighboring regions such that it produces the largest reduction in MDL. For example, like that, we merge the first two regions and keep merging. And finally, there's only one region in the whole space. So which means during this procedure, we produce 4 different segmentations with 4 regions, 3 regions, 2 regions, and only 1 region. And we'll pick the one with the smallest MDL. Okay, so that's the second part. Yes.
Question, so doesn't that mean force that the one with the smallest MDL has to be the one with one region? Because you're always looking for where the MDL is decreasing.
Or it can be the smallest increasing. So we are just pick 2 of this region and keep merging them.
Okay, so it's allowed to increase. Okay,
yeah.
But you understand. Right, thanks.
We may have a curve that decreasing first, and then finally it keep increasing. Yeah, okay. Because the model doesn't fit it well. Yeah. So we just okay. So that's the whole procedure, right? So we know that given the time interval, how could we do the image segmentation? And how could we use backward elimination, the step-by-step procedure to locate the change points? So that's how the algorithm works.
It's a kind of a brute force method, right? You're just going through all the possibilities. Is there some smart way to get the zooming to the optimal region without going through all of them? For example, the whole region probably shouldn't even consider it, because that's probably not going to happen. Is there some?
Actually, this algorithm is already a greedy algorithm. So for brute force, it's kind of like a combinatoric problem, right? So because the region could have any shape, it can be of any shape, and there can be any number of regions. So in that case, it's just more complicated than what we did here.
Okay, so you're already better than the truly naive brute force, but in this region, there's further way of, because as you said, right, it will be decreasing, then it'll be increasing again. Is there some ways that you can get it to that region faster than it gotta go through this whole process?
That's a good problem, actually. Yeah. So So there might be other methods about the image segmentation and based on some different criteria. So there might be algorithms that are more efficient than the current one. I'm not sure. Yeah.
Okay.
So yeah. But still, it's kind of like the whole algorithm is composed of many different parts, right? So we used this image segmentation method to do this part. And we used the backward elimination to help us to find the change points. So maybe we can improve one part by some methods or modify the other part. So, and which might make it more efficient. I'm not sure about that. Yeah, so, but anyway, there's now we just introduced this practical algorithm to find the change points, the image segmentations, and the corresponding Poisson intensities for each of the region. So right now, I have some post-processing. So after these change points are located, sometimes it's of great interest for astronomers to locate the pixels or regions that contribute to the estimation of the change points. So it's kind of like which part in the whole space contribute to that change points, because that part just keep increasing at that time or something else. So we are interested in that kind of thing. So we are pretty interested in these key pixels. We want to identify these key pixels based on what the model is. I mean, based on the model we estimated. So we will just present two methods based on that. Okay, so so the first method is based on the pixel differences. So we just assume that we already have the estimations. We have these lambda hats. And for one pixel, we just assume that its fitted value in the k's time interval and the k plus 1's times interval. And we have these lambda hats. And we can define the difference for this pixel I to be the difference between the square root of these two fitted Poisson intensities. And given that difference, so we have this difference for each of the pixel, then we can somehow calculate the empirical distribution of this differences. For these differences, we can calculate their sample mean and sample standard deviation like that. And then we can define the key pixels to be the one that is pretty large or pretty small than the sample average for these pixels. And we denote these pixels to be the key pixel.
Is the reason you use a square root transformation is because these lambda hat themselves are kind of Poisson? So
Yes.
You're using normal approximation to the Poisson?
Yes.
So,
because lambdas are actually estimated by Poisson counts.
Right.
So square root transformation is really common for Poisson counts because it's a kind of make the variance
Stabilized.
Yeah, stabilized.
Yeah,
Yes.
but did you actually check that? Did you actually do a histogram of these lambda hat to see if the normality works pretty well?
By looking at the square root of lambda hats.
You actually empirically have lots of lambda hats, right?
Yes. It's hard to say, yeah, because these lambdas are the corresponding Poisson parameters are not the same. So when we take square root, it's they have different means. So it's hard to say whether they have the values are the same or not. Yeah, because for the same region, these lambda hats are the same because it's the estimation, it's the average. So,
but you should have a way to demean it to see the normality, right?
How could we do that?
Yeah. So
you've done a lot of simulations, Kong. So I think this thing came out of one of those simulations, didn't it? So it may be that we already looked at these plots and concluded that it was okay, but I don't remember.
Actually, we only tried this method on the real data set, so I can't remember the how could we figure out the variances. Yeah.
Well, if you really believe the Poissonness, then the variance actually is in closed form almost, right? Because it's approximate. The variance is whatever, I forgot. There's a formula. Essentially, it's kind of independent of lambda itself, has
yes.
1 over n minus 3, or there's some corrections to it.
Yeah.
My hunch is this probably is not going to make much difference, but it's nevertheless it's good to double check to see. I mean, there are better approximations to the normality.
Let's say plus 3 divided by 8, this kind of stuff.
Right, there's all these things, which probably does not really make much difference. I think, but here is probably. I think what you really care about is a normality, right? Not much about the stabilize the variance, because you can actually estimate the variance through your procedure itself is a normality. But I guess probably is not too bad. And then also, is the counts tend to be large here?
Counts?
This lambda tends to be large. The lambda can be close to 0.
Lambdas, they are Poisson
No,
Poisson intensities.
Right.
I think we are the condition I think that under which most of this is supposed to work is for what was it, 100
Okay.
counts or something
Okay.
per segment or bin.
So then that probably does not matter because all these corrections plus we divide by a, whatever that these things are, tends to work better for the smaller counts, right? It's not for these large counts, so probably does not really matter that much.
So it just depends on the data set, what data set we are using.
Right.
Yeah. Okay. So that's the first method based on the distribution for the pixel differences. And second method is based on comparing regions. So we can see that, suppose there are two regions, and one region is within the time interval k, and the other one is within the time interval k plus 1. And they have some overlapping parts. So in that case, we can somehow calculate the sample mean and the sample variance for these two regions, and then we can do this kind of test, and somehow close to just comparing two normal distributions, and similarly, we'll do that like that. Okay.
Why do you think they're independent, the mu1 and mu2?
They are from different regions, and they belong to different time intervals.
But your model actually, okay, is a mu1, mu hat here purely, I mean, these are not purely sample averages, right? The model itself use all the data.
Mm-hmm. Yeah.
So it's not immediate to me why they're independent. I mean, if they are purely sample averages from these different regions, then I can see that. But if they're fitted through the model, then the model itself
they're
is
still separated by the change point, right? So this mu1 hat is from the previous change point, mu2 hat is from the next change point, and the models don't cross the change point.
But both models, the models still use all the data, right?
Yeah.
The dependence comes from the data, right?
But given a change point, though, these estimates would be different. Or
the change point itself is being estimated.
The change point is, yes, the change point is being.
So that's data dependent. I mean, you can actually empirically check those things. You can just, since you're doing simulation, you can just check, the correlation between mu and mu hat, over lots of meaning to see if they're independent of each other, to see if there's a small correlation. It might be very weak correlation, but it's not obvious to me why theoretically they're independent.
They might be negatively correlated. Yeah.
Yeah, sure.
Which leads to a change point, maybe.
And so, I mean, the only thing matters you want to check is whether your variance is correctly. Otherwise, you have a correlation term in before you apply the normal approximation, right?
Yeah, that's true.
Yeah. So I would check on this thing. I'm not entirely sure there are, particularly if this thing these regions are next to each other or something.
That's a good one.
But you can empirically check.
Yeah, sure. Yes. Okay, so there are different methods and they work on different scenarios. So, okay, right now, after that, we're just going to talk about the applications to real data sets. So here we already mentioned two real data sets. So the first one is something like that. So we can look at the light curve and we can see that, notice the y-axis is in log scale. So we can see that there's a abrupt change, increase at some time points, and it just decrease after that. And by the way, this one is of a point source. So actually the light curve itself could tell us a lot about the location of the change points. So yeah, so this black vertical lines denotes the detected change points locations. And to be more specific, let's look at this plot. So for part A is actually the data image at time point 42. So yeah, we bin this data as a 64 by 64 image like that. So we can see that it's a point source like that. So, and for part B, this one is the corresponding fitted lambdas. So we fit this one with a piecewise constant function like that. So, and for part C, we can, from the previous light curve, we can see that before this time point, so there is an abrupt change in this time point, and after it, it has a abrupt decrease. So we will use the method we mentioned before to detect the key pixels. And we can see that, so before this time points, there is an increase in this region. And after that, there's a decrease in this region. Here we use blue to denote the increase and use red color to denote the decrease. So yeah, that's how the method works. So we can feed this dataset with a piecewise constant function like that, detect the change points, and then apply the algorithm to highlight the key pixels like that.
Is this a point source?
Yes, point source like that.
Like the angular resolution of XMM is much wider than the actual size of this object.
Yes, so we just keep this, keep some other background informations into this image. So just to see that whether our model could successfully detect what we want.
So what would the ideal thing look like here? I mean, should the entire image should change in time exactly the same way because it's a point source. Is that right?
Yes, you can see that one. So actually, the light curve is just for the points for the whole image is actually the same as the light curve for that point source itself. So yeah.
I mean spatially though.
Spatial.
Like ideally, what should like those two lower panels just look like circles? I mean, shouldn't all of the pixels in that point source be changing in the exact same way over time?
The whole part. So
yeah, if it's a point source.
Yeah, Alex. Yeah, I mean, I think you're right in the sense that it is one single source and that's just flickering. But of course, as you go get into the wings of the point spread function, I mean, you get into low counts and it starts merging with the background. So that's where you're getting the rattiness in the boundaries.
So the locations where the brightness is reduced is coming from it's an artifact coming from the PSF.
No,
right?
it's not an artifact. It's the source dimming.
So source dimming as seen by the instrument, right?
Yeah.
Okay.
Yeah. I mean, this is supposed to be a simple case, right? You have just one point source which flared, and the question is, can you find the points where it went up and where it went down? When it went up and when it went down, and the spatial map is perhaps a bit of a red herring. It should coincide with where the source is.
Okay.
Yeah. So as Vinny said, it's kind of like a simple example, yeah, to illustrate the usage of the methods. Okay, so and then we can look at another one is the okay, this data set, and it's kind of like it's a solar data set, and there's some information about the details about this one. So that's how it looks like. So yeah, so we just use 3 energy bands. So the 3 filters, and so times from this like that. So we can see that as time goes on, there is an object appears in the first time band like that. And also we can find the same thing for the second time band. So for the second energy band, so there's an object.
Kong, a quick question. So I'm confused about what is the sequence? I mean, what is the upper and the lower?
Yeah. So originally you put it in the from top to bottom, but it's hard to fit in this slice. So
Right.
it's from here, there. Yeah.
I see. So
yeah.
Top left is the first one, top right is the second
Second,
time
third,
interval.
first.
Okay.
Yeah.
Got it. Okay.
Yeah. So for all these 3 bands, we can see that there's this image, there's an object of this shape like that. And so for the first 2 energy bands, we can see this object just appeared and keep become more clear. And for the last energy band, we can see that this object appears and then disappear like that. It's not as obvious as it was before. So yeah, for the whole procedure, we just detect 3 change points, and then we can split it into 4 different time intervals. So that's the average images for these 4 time intervals like that. So that's the story. And this one is the fitted Poisson parameters, lambdas. So we fit this real one with a piecewise constant function like that. So we can see piecewise constant function. And yeah, that's the fitted intensities. And yeah, like that. So in that case, it's kind of like, it's hard to find the location of the change point based on the light curve of the whole image itself, because there are many other things. So therefore, when you only look at the light curve for the whole image, it's pretty hard to see what happened here. So right now we just use the method we mentioned before to detect the key pixels. So yeah, so we just apply the method on all the 3 different bands. So we can see that for 1 change point, for the first for an energy band, for the same change point, we can detect that there is an increase with this region. And for the other energy band, we can find that there is a decrease for this region. And this kind of information this kind of result could tell us what happened for this change point during this time period. Any supplementation, Benny?
This is really interesting. Okay.
Yeah,
Just
I
go
mean,
ahead.
I actually, this is, I was hoping that Atre, who's a solar physicist, would weigh in on this one, because, to me, it was quite impressive that it managed to find these things. I mean, clearly, we gave it an relatively easy thing to do, in that we managed to find a isolated loop that didn't do much. But the fact that it still managed to do the right thing was quite comforting.
Yeah, I have a couple of questions. So, so the model shows like, is it taking the AIA response?
Right.
But
not the response, just the images.
Yeah, response in the sense the PSF. So when you convolve it, but I see still some sort of a blurriness. Is it coming from the model which we do, or?
The blurry, no, it is not. The blurriness is from the fitting. meaning that it's the original data or AAA directly. And then you find these segmentation in spatial segmentations. Those are sort of grouped pixels. So that is probably what you're seeing as blurring on this scale.
Okay, on the spatial scales.
Yeah, so there are segments that sort of group. Okay. Yeah, can you zoom in a bit, Kong?
Yeah.
Yeah, there you go. So they're not really, it's not really blurring so much as regions that have been pulled together into related segments.
Okay.
Because we use piecewise constant function to fit it. That's the reason. Yeah.
Yeah, this is, so if I just wanted to make my understanding correct. So you have 4 time bins here. So, and the loop which is shown here was clearly seen on 3 different bands you're using, wavelength bands. And you try to identify a change point from the light curve, and then you have identified 4 of them. The flare was looking, or the loop was brightening, that was identified here.
Right.
And that is identified in one of the hottest wavelength, which is 94, which is what is shown here. And you showed that with the time you identified the pixels where the brightening occurred.
Right. Well, we looked at 94, 131, and I forget the other one, 211, I think.
Okay.
Actually, we also looked at 335. Sorry, we looked at all 6, as a matter of fact, and it didn't really change the results. But these happen to be the biggest signals.
Okay. Yeah, this is pretty impressive. So, so we are able to identify the pixel location where these bright emissions occur in terms of the in the case of sun, because it's an extended source. So whereas that cannot be done for a point source. Am I right? So for point source, you can identify the time domain where the change points occur, whereas you cannot say which pixel the brightening happened. Am I right?
Right. Right.
Okay.
That's the idea. Yeah.
Okay.
Okay. Yeah.
Hi. I also have some questions about that result. I'm from University of Michigan. We use these AI images for solar flare prediction, actually. So is the point source you are detecting here a solar flare?
No.
In this case, no?
No. Well, first of all, it's not a point source. It's a loop.
Oh, it's not. Okay.
Right. So the point source was Proxima Sun was the other example observed with XMM. But this one, wait, what happened? Okay, sorry, Kong, can you go back to the image?
Oh, sorry. This one?
The next one, and the next one. Yeah. So what this this just happened to be an isolated loop that filled while we were looking at it, and it brightened for a while and then went away.
Okay.
And nothing, and the reason we chose this was basically because there was nothing else going on surrounding it. So it was essentially a test for the algorithm. So before it sort of goes into production.
Right. I see. So, yeah, go ahead.
No, I was just saying. So this is like if it failed on this, then it would have no hopes on anything else.
Right.
But it worked. So now we can go to the next step, which is run it on more complicated regions of the sun.
Yeah. So one more question is that in this case, so you have the true images, right? And then you fitted the model and you have the fitted results. So is this model able to do forward prediction to detect, for example, future, say, loops or change points?
I'm going to say no, but Kong might have something different to say.
Because you have a fitted Poisson process, right? In principle, you can simulate it, right? Forward into the future, right?
Each change point between each change between the change points, it's assumed to be flat, right? It's piecewise continuous.
Okay.
In a sense, we can isolate the pixels in this loop, for example, and see how things happen before and after, and try to make predictions, I suppose. But I have not really thought about it. But I don't know. And Kong might have some statistical insight on that. Kong.
Okay, so usually with change point, it's like a afterward analysis on the procedure. So just want to find what happened during this time. But for the forward thing, we don't know whether there will be a change point later on or something like that. So it's hard to say.
Yeah, may I jump in? Sorry, I joined later.
I didn't realize you were here.
Yeah, I joined about page 15. So that's a very good question to predict a change point, but I can tell you very high confidence that it's very hard problem. Okay, if anyone can do that, they can make a lot of money in the stock market when you can predict a market crash or market up. So yeah, that I know people working on that. It's hard.
I see. Yeah.
So I have a question. So this is a single loop brightening. So there are two thoughts in my mind. So one is like when you say the change point, the prediction of change points. So right now, since it is piecewise continuous, so is it like when you want to predict, even for example, the flare, the next, how the flare is going to evolve. So for that, you need to bring the physics between the change point number 1 and change point number 2. Right now, that is not here, right?
Yeah.
And that is dynamic, which is not easy to incorporate. Am I right?
Yeah.
And second is when we say like if you want to extend this for from a single loop brightening to a loops evolution like a microflare or flare. So, but how well we can use this method, because now we assume in a change point time interval delta t 1, you have mu1 and sigma 1, which is independent from mu2 and sigma 2. Whereas when you look at a flare, the evolution, the emission which you see in time domain delta 1 is a cause which is going to affect the next. So they are not mutually independent, right? So would that change that?
The independence here is a statistical thing, right? I mean, so the intensity, yes. I mean, as you, think of fitting a spectrum. You might have a Bremsstrahlung continuum going across multiple bins, and there's a model connecting the intensities, but the counts that you see in each bin are independent.
Okay.
So that is the independence that is being used here. It is true that, yes, one could, in principle, imagine an underlying model for the increase in the intensities. And if you do that, yes, you might be able to predict what happens next.
Okay.
But yes, that we haven't done anything like that.
Okay.
At this point, it's very simple, just piecewise continuous modeling of the intensities in small isolated regions.
Sure. And how can you comment on how good spatially you can identify in AIA?
In principle, you can pick up events that happen at AIA resolution, but unresolved events, right? But it's just a brightening, it shows up. But the question though is, would you believe it? Because there's always going to be fluctuations, and unless you can see something that is that you can essentially track with your eyes, no solar physicist is going to believe anything that comes out of this. So that was in fact the purpose of this exercise, to see that, okay, here is a loop that brightens before our eyes, and will the algorithm pick it up?
Okay. Yeah, this is really interesting, because when you say it goes at the spatial scales of AIA, I was thinking like then maybe we can identify some of those loops, and then to make sure that they are physical we can probe their emission measure using multiple wavelength. Of course, not at the AIS scales, and to make sure that the evolution which you see is either correlating or shows any evolution in the EM emission measure. That's interesting.
Exactly. Yes. Those are in long distance future plans.
Yeah, that's great.
Actually, there is one other interesting plot that I think Kong has. Yeah, that one. So those are the light curves of these isolated. Oh, Kong, sorry, I should take over your presentation. Go ahead.
Oh, please. You're more familiar with it than me.
No. Please continue. Go ahead. This is your topic.
So yeah, we just want to see whether these detected key pixels are meaningful or not. So we just pick these regions and plot their light curve and compare the light curve with the other part, which means the background. So we can, and also here we just denote the location for the detected change points here. And yeah, so we can see that. So apart from this detected key pixel regions, for the background, the light curve seems to be flat or does not change a lot. But we can see all these changes are pretty obvious or significant in the detected regions. Yeah, maybe please go ahead.
Yeah, no, so Atre, actually, I mean, you've seen these cases where we have tried to look for isolate small changes in the light curve, right? So the major advantage of this is that if you, instead of looking at the full field of view, if you isolate it down to the few pixels where this change is happening, then you can pick up just that event, the change just due to that event, and essentially ignore the rest of the field. So it lets you focus on a particular event that might have happened without too much interference from the background, and increases the contrast so that the intensity fluctuations pop up very obviously. If you looked at the overall light curve, including these pixels, it won't show up like this, right? Because this is in dn per pixel, average over just those key pixels.
Right now, the selection, sorry, so the selection is done manually, am I right? So
no, the selection is done through the algorithm. So the key pixels that are found here in this figure, those are, so the union of those pixels gives you this light curves.
Light curves, okay. It's impressive. Yeah.
That is the part where I was impressed. Yes.
Yeah, it's really impressive. Yeah, it's great.
Yeah. Okay, so that's this example, and so for some future works, possibly we can, right now many statisticians just ask me a question like, so how significant or how confident you are that this change point is actually indeed a change point. So it's kind of like we want to quantify the evidence of the existence of the change points. So, for this algorithm, it cannot tell us this kind of information. So it might be helpful to derive a test statistic based on maybe Monte Carlo simulations or other methods to quantify the evidence of the existence of a change point. So that's one possible extension. And another one is so right now we use the assumption of piecewise constant functions. So in practice, it might be better if we could allow piecewise linear or even piecewise quadratic for the modeling, so that model could work better in the practice. Yeah. So these are some possible extensions for the current method. Okay, so that's all for the presentations. And okay, thank you guys. And any questions?
Yeah. Thanks, Kong. Very well done. We have also run out of time, but of course we are, if there are questions, in principle, we can stick around for a little while longer. So
we did have a question for Chong now. Thomas is here. We can see if
oh, you
Thomas...
can ask him about MDL. Yes.
Right. No, I mean, I talked to Thomas quite a few times. I'm still trying to understand it. But this is a special. I don't know if you, Thomas, you heard. We were talking about like how do you code these regions, right? The first part of the MDL, and it seems like that depends on, how you code it. But that seems like a variation that shouldn't really matter for which changing point, right? Because that's additional human introduced, kind of variation. I think I understood from Chong's response is as long as you code consistently with different models, you probably can keep their order. So in that sense, it probably should be invariant to how you code it. Although I'm not entirely sure, because if one model is more complicated than the other, for someone like me, I could code it really badly. I guess the question is whether this first part really meant to be the best coding, like to be used, and not just for any coding.
Yeah, so that is always so-called challenge or criticism of the MDL method. Okay, and now I've used it for so long. Now, what if I get a question like that? What I would say is the following. Okay? So I see MDL is a method, okay, for us to generate model selection criteria, like objective function that we want to do. Now, in the process, you may, when you generate a model, okay, there are different ways to. It's true that there are different ways that you can encode what you want to encode. Say for this one, we are not encouraging the boundary has to be smooth. We can do something like that to also penalize the smooth of the boundary more. Okay, if we believe the true model is smooth, we can do that.
Yeah.
Now, but then what I'm going to say is like MDL is like a procedure or methodology, or you can even treat it as a black box. You put in something, you put a handle, okay, it gives you a criteria. Now, it depends on how you do the handle, or what kind of grease you put in the handle, right? It can give you something different. Now, but then my experience is that as long as you do something reasonable, the model selection criteria that you get at the end will give you something very reasonable also. But I think what is very important actually is no matter what criteria you have, we should at least study the theoretical properties. And that's why Con did the consistency. Yeah, and then another thing is like, I try like using different handles, so I get something slightly different MDL criteria. But when I look at all these MDL criteria for the same problem, the leading penalty terms, okay, they are always of the same order. Okay, so asymptotically, there may be finite sample differences, but that's just depending on the way you do it. But asymptotically, or when we look at the leading order, they will be the same. So I'm not defending MDL. I'm just saying this is my experience, and I still find it's quite useful in a lot of things. And then I should say this is only one version of the MDL principle. There are different versions. Okay, this is one of the earliest versions, and it's the easiest to use. There are other versions they claim to have, or they prove to have better statistical performance, but very often it's just harder to calculate. And it may involve like you need to integrate a huge integral. Yeah. So
I mean, I completely get it what you're saying. I think for me, what's interesting here is that clearly there's some really good property of the methods, as there's some kind of robustness. It's the part which is kind of interesting is like any methods, as you said, right? It depends on what grease, what oil you put in. Like all methods will depend on the person's skill to implement, right? When you say the model, whether the model is wrong or correct. But what's interesting is that this criteria has explicit as a part. Maybe that's a part I'm trying to get it to, whether that's actually I'm thinking the right way. There seems like there's explicit part of it was actually really should not matter. It's so what I'm trying to say that the original proposal there is like, is it a requirement like this first part of this coding part? It has to be the minimum kind of a, the best code you can put in. Is not just say any way of coding it will make this criteria make sense. Is there such a requirement? Then of course in implementation people have a different approximations. That's entirely fine. Like all the models we do is approximation. But is there like this? Was the original proposal meant to be for the best available code?
Yeah, the Switzerland said something like that. So there are two requirements, right? The code cannot be redundant. You shouldn't repeat.
Sure.
You shouldn't use more than what you should do. And then secondly, the code should be enough. You should be able to recover the object with the code. So you cannot oversimplify. So it cannot be too small and then you can be too large.
Okay. I see
right there. That's what it says.
Yeah. Okay. Now got it. Yeah. That's what I was thinking. Yeah. So it cannot be redundant. So there is a requirement there, and
yeah.
Right. Okay. That makes sense. All right. And so it's 1:30 now.
One quick thing before Atray leaves. I just want to point out that I mentioned to Kong in the data sets that I gave you, all the data were labeled Atray, FOI. This is that Atray.
All right, so this is the guy that you can blame if any data is wrong.
Oh, right? Yeah.
Yes, exactly.
now you know the source of say something did not work for your methods. Ask him to give you better data. Okay.
Yeah.
Yes.
Yeah, I can
actually
produce
he's
another
working on
bright loop.
Yes. No, he's actually working on generating better data from what I understand. So
great.
Next time.
we're always happy. Quick question, Vinay. We are meeting in 2 weeks. Is that right?
No, Anita, I think we don't have anything scheduled until April.
We're looking for the volunteers and schedules, and we'll have to set up something. Maybe we will.
Yeah. Wait. I saw last time we actually set up almost the thing as like full schedule to moving forward.
Yeah, we did talk about it.
We did talk about it. Was it that I saw that we have like every